Okay, so in this tutorial, I will teach you what the results of the gene expression calculation mean. Okay, so in the previous tutorials, I have shown you how to enter the correct directory in order to run the GUI. Now, what I've noticed is that if you are if you are in MATLAB 26, then you'll have to write this URL, MATLAB 24, the input, etc., etc. But if you are in MATLAB 24, which is where the codes can be found, then you don't really need to write MATLAB 24 beforehand. You simply write the and then dot dot and then input HILA candidate genes. Okay. Yeah, and we're currently in the correct directory. Again, go to candidategenes.gui, run the code. Okay. Choose a dataset, applet file. I'm just randomly choosing a file. Okay, driver gene met, output images, and we will output all the images. We don't have many images in this part of the calculation. Choose output directory. I will output it to test. Okay. Now choose gene expression calculations. In the previous tutorial, I have explained the Kaplan-Meier expression and co-expression. Okay, so click done. Then you'll see the code running. The Excel files were successfully terminated. You will soon see the code outputting images. Okay, and meanwhile, I will show you what you are supposed to get. Oh, yeah, okay. So while this calculation runs, you will get, I cannot, you will get these figures open. These are clustergrams, and usually in my code, if I print figures, they are invisible. In the clustergrams case, they could not be invisible. I could also not change their name. As you can see here, here it is called clustergram 4. And usually the names are more descriptive. And as you can see here, it says saving images, saving all images. And you see the names of the images being saved. And now we will wait until it is done. Also, please do not close the figures while the code is running. If you close the figures, the code will simply crash. So don't do that. Okay, and we are done. Okay, Okay, now let's see what we got. So in this calculation, we get five Excel files, okay? And the main plot that you want to look at is a bar plot graph. And for example, this plot. Okay, so what you see here is, in this case, we separated our cohort or the patients into patients which have high expression in MET and the rest of the patients, or patients which have lower expression in MET. Here I didn't really indicate whether low is rest or actual low expression. It would just make the code cumbersome, and you can easily change that via the GUI in MATLAB. And okay, so, oh yeah, and I output graph with only the significant genes, and I also have a graph with all the genes, and I'll explain what it means to be significant soon. Okay, so as you can see in the blue group, which is the group of patients with high MET, you see here that, yeah, true. The average expression of all the patients in MET is this value, and the average expression of the group with the low, or the rest of the patients, is lower. Look at the red group versus the blue group, and you can also see the standard error of the groups, and the results are compared by t-test. Okay, and what we are trying to find is that with this separation that is based on the expression in the driver gene, in this case it's MET, we try to see if there is also anything significant with other genes. And it's quite hard to see if there is any difference when you separate by MET, if there is any difference in other genes. Perhaps TMBIM6. And let's go to the table of this graph and look what it is. So it was a bar plots, and their p-values. We split by MET with patients with high, 20% of the patients with high MET versus the rest, which is 80% of the patients. Okay, and here you see in the first row, you see where the file, the data came from. The data was split according to MET. The high percentage was 20, and the initial number, the number of the patients in this group was 381. If you take 80% of the patients, you have 1,520 23 patients. So here you see gene names. Whoa. Okay. The average expression in the group with high MET, average expression of the group with low MET or REST, and standard error of the group with high MET, standard error of the group with low MET, and then p-value, which was calculated with t-test. And the results are considered significant if they are smaller than 0.05. Okay, and you see that there are many significant genes here, and the most noticeable are perhaps FAM98A and TMBI-M6, but you might want to take, you might want to consider genes which also have a p-value that is lower than MET, yeah, because you want to see if by separating by MET, you get a better separation in expression in other genes. And okay, so let's look at what happens when we separate, when we take 20% of the patients with low MET. Okay, in this case, also FAM98A was substantially significant. So I don't know, perhaps it means that there is the gene itself goes hand in hand with MET expression or not. Perhaps it has high variance between the patients. And again, in this time, when I say top percentage, I mean the percentage, the number of patients. The patients which don't have low MET, and low percentage is the 20% of the patients with low MET. We can look at this graph as well. So we have bar plot with 20% patients with flow MET. Okay, and here we can see that there is a difference indeed in MET, but it isn't so clear with the other genes. Maybe this gene, I don't know, which is FAM98A. I also have graphs, box plot graphs. But it's not as static as the bar plot graph. And as I said before, I also took graphs with only the significant genes, because sometimes people give me more than 400 genes and the plot is just too cumbersome. So you can simply, reduce your plot to only the significant genes. And here we also have, in this calculation, we also have some graphs which are not summarized in an Excel table. For example, this clustergram. And clustergram is basically a dendrogram which links in a certain way, which I can elaborate later on how it does so. The genes and the patients. I do not need to cluster the patients, but I do. And you can define it to not do so. It's not really important. For example, here you can see that tuba AB and tuba AC are clustered together, and if we in terms of expression, yeah, the clustering is based on the expression. And if we look at MET, we see it is clustered with this group, with BIRC6 and FAM98A. And also, I did a clustergram. Oh yeah, and a clustergram is also a heat map besides a dendrogram. I also took only 20% patients with a high expression in MET and clustered together and looked at how the genes are clustered now. I also did calculation when the patients were, when I took only 10% or 30%, but for some reason, the thumb of rule in the lab is to take 20% of the patients. I have no idea why. And it's worth checking. Yeah, this is another calculation, which is not done in this case. Let's see something that is relevant. Oh yeah. Oh wow, okay, so this graph is not that clear. Perhaps let's look at it different. No. Okay. So I was also asked to do a normalized gene expression, sort of, you can say heat map or scaled image, but it's not, there is I get a normalized, sort of normalized, I didn't need to normalize anything, and I get different results if I try to normalize the data. So I don't do that. The title here is normalized, but it isn't, and I didn't change this title because seriously, this graph isn't used. Pretty sure Elon already forgot about what he asked me to do. He called it normalized, but it isn't. But never mind, it's not that important. It's just a way to see the data in scaled way, I would say. And that's it. So that's it for the gene expression calculations. What Elon usually likes to do is, for example, he likes to take the average of one group and divide it by another. Okay, and then he sees, for example, if we take the group with here it is, we take lower percentage of MET and 20% patients with low MET, you can see it here, and the rest of the 80% patients. So we do expect to see, if we divide the lower average by the higher average, we expect it to be below 1, and obviously the lower it is than 1, the better, or or if it's another gene and not the driver gene, so we expect it to be a value that is significantly higher than 1. But you have to be careful with that, because you have to look at your data beforehand, and if you'll have, for example, a normalized data with values surrounding 0, and you have values that are negative, then that wouldn't really represent, I mean, a division wouldn't really represent the fold change, I would say, of the data. It's because if you have, you would agree with me that having an expression that is -3 and 3, and if you'll divide them and get the absolute value, will get 1, and you will agree with me that the distance between them is quite significant. It's 6, and if you'll divide 2 by 1, if you'll have, if you'll have an expression that's 1 in the lower group and expression that's 2 in the higher group, and you'll divide, let's say, 1 by 2, then you'll get a fold change of half, and it will have, you will think that, you know, fold change that is significantly lower or higher than 1 is more relevant to your results. But if you have negative values, you'll have to be careful with that. You'll have to be careful. It usually doesn't happen, okay? But usually the expression values are positive, and I'll later explain how the expression values were calculated. But yeah, that's it for now. And yeah, goodbye.